I welcome all of you to our fourth lecture on the deflection of the beams. The question that we have is about a simply supported beam, and this simply supported beam is being subjected to a concentrated load of magnitude 6 kilonewton at a distance 2 meter from one of its end called end A. It says determine the maximum deflection of the beam. First of all, before we determine the maximum deflection of the beam, we should know the equation of the deflection curve. We know the equation of the deflection curve is obtained once we solve the differential equation EI. EI is called fluxural rigidity. D2 nu by dx2. Nu is the deflection of the beam. EI d2 nu by dx2 is equal to the bending moment M. So in order to solve this equation, we should know the right hand side. That is, we should know what is the value of the bending moment. As far as the beam is concerned, the beam is concentrated, simply supported beam subjected to concentrated load of 6 kilonewton. In order to solve it, first of all, we should draw the bending moment. And we know, first we'll be taking the section which will be varying from point A to a load of 6 kilonewton. And second section will be from a load of 6 kilonewton to end C. Because we know that we are having a concentrated load, and we know the point where the concentrated load acts is the point where the bending moment changes abruptly. So there will be an abrupt jump of the bending moment as we go from left hand side of 6 kilonewton to right hand side of kilonewton. So we have to take two sections. As far as the section 1 is concerned, the section 1 will be like, our first section will go from, this is our x is equal to 0, this is the starting point, this is our x is equal to 0, this point, and this point is our x is equal to 2, and this point is our x is equal to 3. Okay, this our x is equal to 3 meter. So for a section which varies from uh, from this section to a distance of 2 meter, and another section will be varying from a distance of 2 meter less than or equal to a distance of 3 meter. This is what we have to do. Now what we will be doing, first of all, we have to find the bending moment, and we know in order to find the bending moment, first of all, we should be knowing the reactions. We know the reactions. First of all, we have to find the reaction at end C. We have to find the reaction at end A. We'll be calling this as reaction of end A as RA and reaction of end C as RC. Okay. We write the equation of equilibrium. We know RA plus RC is equal to the load acting downwards, that is 6 kilonewton. This is our first equation of equilibrium. Or we can also write RA plus RC minus 6 kilonewton is equal to 0. That is RA plus RC will be equal to 6 kilonewton. We'll call this as equation 1. The second will be taking moments about an axis passing through point A. Will be moment because of the 6 kilonewton. The moment because of the 6 kilonewton will be 6 kilonewton multiplied by 2 meter. And this is trying to rotate our beam in the clockwise direction. We'll take this as minus. And the moment because of RC, it's trying to rotate the beam in anti-clockwise direction. We'll take this as RC kilonewton multiplied by 3 meter. Okay, this is 3 meter. So this has to be equal to 0. So this is 12 minus 12 kilonewton meter is equal to minus 3 times RC meter. So meter and meter cancel, minus and minus cancels. So RC becomes equal to 4 kilonewton. So it means the value of RC is equal to 4 kilonewton. And since RA plus RC is equal to 6 kilonewton, when RC is equal to 4 kilonewton, therefore RA will be equal to 2 kilonewton from this equation. Okay, therefore our RA is equal to 2 kilonewton, RA is equal to 2 kilonewton, and our RC is equal to 4 kilonewton because the summation is equal to 6 kilonewton. So we are successful in finding the reactions RA and RC. This is in fact our step number 1. Once we are finding the reactions RA and RC, now we'll be writing the equation for the bending moment. We know for this section, for x greater than or equal to 0, less than 2 meter, that is for a section AB, okay, we take, let's take a section here. We know now RA and RC are known to us. We will in fact write it here, and the value of our RA is equal to 2 kilonewton, and our RC is equal to 4 kilonewton. This is quite known to us, no problem with this. Now in this section, what we will write, we will draw a section. Let's draw a section over here. And once we are drawing a section here, so we'll then write, let this distance be our x. He has written x1, it's okay, no problem with it. You can write x, you can write x1, no problem. Let's write this distance as x. Okay. So let the shear force here be V, and let's suppose the bending moment here is M. This bending moment we have to find. Okay. Write down the equations of equilibrium. We will write this RA is acting upwards. This RA is acting upwards. We'll write RA acting upwards minus V, and there is no force acting in this section. This is equal to 0. Therefore, V becomes equal to RA, and RA is equal to 2 kilonewton. So this is V is equal to kilonewton. Okay. So this is the value of our V. Now we will find the value of the bending moment M. Taking moments about an axis passing through point A, we'll have the anti-clockwise bending moment is M. We'll write this as positive M. The moment because of this V about an axis passing through point A will be V into X, but this will be negative because it's trying to rotate the beam in clockwise direction. This is V into X. There is no other force creating the moment. This is equal to 0. Therefore, in this section, the value of the bending moment is V into X. Since our V is equal to 2 kilonewton, therefore M becomes equal to 2x. Okay. Therefore, the bending moment equation in this section, from A to B, the bending moment equation is M is equal to 2x. Okay, kilonewton meter. This is for this section. Now we'll obtain the bending moment equation for this very section. The bending moment equation for this section will be, again, we have to take a section. Taking a section somewhere, taking a section now somewhere here, and we write, let the shear force here be V, let the bending moment here be M. Okay, and let this distance where we are taking this section, let this distance be equal to X. Okay. Now for this section, our section is restricted. The value of our X goes from X is equal to 2 to X is equal to 3 meter. That is where in this very region. Okay, where in this region our X varies from here to here. Okay, so as far as the equation of the bending moment is concerned, we can write the bending moment equation is, first we'll write the equations of equilibrium. This is our RA. This is RA, which is equal to 2 kilonewton. The equations will be RA is acting upwards. We'll write this as RA. And this 6 kilonewton is acting downwards. We'll write this as minus 6 kilonewton. And this V is also acting downward. This is V is equal to 0. So RA, we know it's equal to 2 kilonewton. Okay, so this is 2 minus 6 is minus 4. Therefore, V will become equal to 4 kilonewton. V becomes equal 4 kilonewton. Okay, so this is the value of our V. But this V will be, by the way, minus 4 kilonewton. Because this is 2 minus 6, that is minus 4. So V becomes equal to minus 4 kilonewton. This is the value of our shear force. Now taking moments about an axis passing through point A, okay, we'll be having moment. First of all, we have the moment M, whose magnitude we have to find. We have M. And then we have the moment because of this V. V is minus 4. This will be, it's trying to rotate it in, since this V is coming out to be minus, it means we have to reverse the direction of this. We have to reverse the direction of the shear force here. This V is minus 4, so it means it's the direction which we have selected is not correct. This V will be in the upward direction. Okay. Now its moment will be V into X, but this will be positive now because it's trying to rotate the beam in the anti-clockwise direction. So that will be plus V of X. Then the moment because of this 6 kilonewton will be 6 kilonewton into 2, but minus, so it will be minus 6 kilonewton multiplied by 2, and there is no other force creating the moment. This is equal to 0. Therefore, as far as the value of m goes, m will become equal to minus Vx plus 12. Okay, minus Vx plus 12. As far as our V is concerned, our V is equal to minus 4. So it will be our V is equal, as far as V is concerned, V is equal minus 4. So it will be 4x plus 12. Okay, 4x plus 12. Since we are reverting the direction here, therefore this we will not be writing as plus, sorry, minus. We have to maintain the direction because we have said V is equal to minus 4x. Okay, then we have changed the direction of the V. Therefore, V for us will be now positive. So therefore, minus Vx, our V is 4. This is, therefore, if we take this 4 out, it will be 4, and inside will be 3 minus x. Okay, this is the bending moment M in our section. So in this section, in another section, the bending moment equation is m is equal to 4 times 3 minus x. Okay, this is what we have also. If you look at this, this is already here, and if you look at this, m is equal to 4 into 3 minus 6, this is already here. Okay, so these are the values of the bending moment. We are successful in finding the equations of the bending moment. Now let's go ahead. After finding the equations of the bending moment, what we will do, we will use this moment curvature relationship. We'll use the deflection formula for this beam. As far as the deflection formula is concerned, we know the deflection formulas are like the deflection formulas are EI. So now we have two bending moments, so we'll be essentially in two sections. First, we'll be in section for x going from x less than or equal to 2 meter. In this section, we have EI d2 nu by dx2, EI d2 nu by dx2 is equal to bending moment equation, and bending moment in that equation is 2x. Okay, it is 2x. Okay, therefore, if we integrate it once, we'll get EI. Integrate this equation once, EI d nu by dx, EI d nu by dx is equal to, this is 2, integral x is x square by 2, 2 and 2 will cancel. This is x square plus constant of integration c1. Okay, we'll integrate it again once more, we'll get EI. Now we'll get integral dv by dx is nu. This is the equation. This nu now gives us the equation of the, this gives the equation of the deflection curve. Since this will be in terms of x, we can also write this as nu as a function of x. Nu is a function of x. Integral x square is x cubed by 3. This is x cubed by 3 plus c1x plus one more constant of integration, that will be c2. Okay, therefore this equation and this equation are very important equations for us, because this equation tells us about the slope. d nu by dx is the slope of the deflection curve, and this gives us the equation of the deflection curve in the region going from x is equal to 0 to x is equal to meter. Now we'll go ahead, apply the equations for the deflection curve for x going from 2 meter to x going to 3 meter. The equations for the deflection curve will be equations of the deflection curve are EI d2 nu by dx2, EI d2 nu by dx2 again is equal to, the bending moment equation is 4 times 3 minus x. Okay, 4 times 3 minus x, this is in the other region. So what we will do, let's perform the integration once. Let's perform the integration once. If we went on to perform the integration, the integral of this will be EI integral d2 nu by dx2 is d nu by dx. This is d nu by dx is equal to 4 into 3 is 12. So 12, this will be 12 x minus 4 x square by 2 plus constant of integration c1. Okay, We'll perform one more integration. That will be ei nu as a function of x, d nu by dx integral will be nu, ei nu as a function of x, nu as a function of x is equal to integral 12 x is 12 x square by 2 minus, this is 2 and 2, this is minus 2, integral x square is x cubed by 3, integral c1 is c1x, and one more constant of integration c2. Okay, since we have already initialized the two constants of integration c1 and c2, in place of c1 we can write here, we will not write c1 and c2 here, we will initialize them by some other, we'll call this as c3. So this is c3x and this constant is c4. Okay, so now we have four equations. We have this equation. Okay, the equation is here. We have this equation is here. We have this equation third, uh, this equation is here, and we have the fourth equation. That equation is here. Okay, so we have the we have the equations of we have these equations now, four equations, and we have to solve all these four equations. Okay, to obtain the values of C1 and C2. Okay, so what we'll be doing, if I clear all these, because whatever we have written on the screen, that's already here. So more importantly and essentially, we will be focusing on this equation. We'll be focusing on this equation because this equation is our this equation, except for x being variable. Here we have variable x1. This is same. Okay, whether you have x as a variable or x1 as a variable, we know this x1 or this x is restricted for x going from 0 to 2 meter, and this x2 is restricted for x going from 2 meter to x going from 3 meter. Okay, we know it now, and we'll be this equation will be under our focus. It's our this equation which we have derived. This equation, this is this equation is our this one. Okay, and this fourth one is here. Okay, so these four equations we'll be using, and we'll be rubbing up whatever we have drawn till now. Now, in order to find the values of these constants of integration C1, C2, C3, and C4, what we have to do, we have to apply the boundary conditions. See, the boundary conditions that have been applied are, the boundary conditions are something we need to understand first, how these boundary conditions are given to us. It says the four constants are evaluated using two boundary conditions, namely x1 is equal to nu is equal to 0, and at x2 is equal to 3, nu2 is equal to 0. That is quite evident from the figure here. Look at I have been saying that at the supports there is no deflection. Even if when the beam is subjected to loads, the beam will deflect like this. Okay, so the deflection curve of the beam will be like this. Okay, at these ends, at end A, at end C, there is no deflection. Okay, this point was initially here before the application of the load, and after the application of the load, the point is still here. This point was initially here before the application of the load, and even after the application of the load, the point is still there. So we can write that at x is equal to 0, at x is equal to 0, the value of our deflection is 0. This is fine. And at x is equal to 3 meter, the value of our deflection is again equal to 0. But now the question arises, when we use at x is equal to 0, the value of our deflection is equal to 0, this equation will be using in this case. Okay, this one. Okay, you know why? Because this is the equation which is valid for this region. This equation is valid for the region going from x is equal to 0 to x is equal to 2 meter. So once we substitute the equations that we have, the equations that we have in hand, we will be coming up with, let me apply the boundary conditions. First boundary condition is at x is equal to 0, the value of our deflection is equal to 0. Okay, the value of our deflection is equal to 0. So we will be using this equation. This equation is be used because this is the equation that is valid for a region going from x is equal to 0 to x is equal to 2 meter. Since x is equal to 0 belongs to this region, therefore this equation is to be used. The value of the deflection is 0, therefore left hand side is 0. The value of nu is equal to 0, left hand side becomes equal to 0. X is 0, this x is 0, therefore from this equation you will get the value of C2 is equal to 0 directly. Okay, once we substitute the value of x to be 0, x is equal to 0, nu is equal to 0, therefore what remains is C2, C2 becomes equal to 0. Therefore we have obtained the value of C2 is equal to 0. Now going ahead, we know at x is equal to 3 meter, the value of our deflection is again equal to 0. But this value of x is equal to 3 will not be using this equation. Now we'll be using this equation. The reason being that this is the equation that is valid for the region going from x is equal to 2 to x is equal to 3 meter. So substitute the value of the deflection is equal to 0. So the left hand side of this equation becomes equal to 0, becomes equal to 4 times 3 by 2 x2 square, and our x2, as far as our x is concerned, the x takes the value of 3, that is 9 by 2. Or I can do one thing, I can directly show you what has been solved here. It's here. So as far as the boundary conditions are concerned that we have in hand is that's what we have done. At x is equal to 0, our first C2 becomes equal to 0, we have done just now. And at x is equal to 3 meter, okay, apply, substitute the value of x is equal to 3 in this very equation. Substitute x is equal to 3 in this equation with left hand side equal to 0, because at x is equal to 3 our deflection is equal to 0. What we will obtain is we obtain left hand side is equal to 0. Substitute the value of x is equal to 3, C3. Therefore we will obtain some equation that will be in terms of C3 and C4. Okay, so we have an equation in terms of C3 and C4. So our C2 is equal to 0. Our C2 is equal to 0. We have found the value of C2 from previous. Now we have to find the value of C1, C3 and C4. These are the 3 constants of integration whose value is to be determined. So what is to be done? Look, we need some other conditions for it. If you look at the curve, the deflection curve has to be constant. It has to be continuous from point A to point C. Okay, and as it has to be constant from point A to point B, as described here, as given here, it has to be constant from at all the points. It has to be continuous from these points, from point A to point B. Then, so if you look at the point which is at a distance of 2 meters, that is at this very point, okay, what is happening? The deflection curve at this very point will be, the deflection curve has to be a continuous curve from going from x is equal to A to x is equal to C. The deflection curve has to be something like this, okay? So it means if you look at the point B, which was initially here, now because of deflection has been moved here, okay? Now this point B was the point where our division took place. We were on the left hand side of this point B calculating the deflection using this equation of the bending moment, and we were on the right hand side of this 6 kilonewton force, or to the right hand side of this point B, and we were calculating the deflection using this equation of the bending moment, okay? But what is at point B? At point B, okay, the deflection by the left hand side should be equal to the deflection at point B. The value of the deflection given by the equation applicable on the left hand side should be equal to the value of the deflection given by the equation valid on the right hand side, okay? That is, I mean to say, at point B we create the division. In fact, we said that on the left hand side of point B you will have one value of the bending moment, that is this, and on the right hand side of the point B you will have this value of the bending moment, okay? So it means The value of the deflection curve, the formula for the deflection curve, that is this formula for the deflection curve is applicable for the left hand side, and another formula, that is this formula, another formula, that is this formula, is applicable for the right hand side. But once we are at point B, once we are at the point B, what should actually happen? At point B, the value of the deflection given by the equation applicable on the left hand side should be equal to the deflection at point B given by the equation applicable on the right hand side. That is, equation applicable on the right hand side should give the same value of deflection at point B as the value given by the equation which is applicable on the left hand side of this beam. Both the equations should give the same value of the deflection. Otherwise, if two equations do not give us the same value of deflection, for example, the equation which is applicable on the left hand side tells you that the deflection of point B is, say for example, 0.1 mm, and the equation which is applicable on the right hand side tells you that the deflection of point B is, say for example, 2 mm. Okay, so it means if you draw the deflection curve, this deflection curve will have a kink like this, which is not possible. This type of kink is not possible in the deflection curve. It means the beam is bending and its bend is like at the same point it is having two values. Okay, this is not possible. Okay, at the same value of x, the values of the deflection are 2, which is not possible. That is, at this value of x, somebody will say that this is the value of deflection or this, but beam will have only one point. At x is equal to 1, the position of the beam will be specified by a single point, not by 2 points. So it means the clear idea is that the value of the deflection given by the equation on the applicable on the left hand side should be equal to the deflection at point B given by the equation applicable on the right hand side of point B. The two should give us the same values of the deflection. Okay, that means if we have then obtained our next boundary condition. Okay, and the boundary condition that we have obtained is like this. If we draw the deflection curve, the slopes will be same. In fact, or we can write the deflection curve is essentially like this. The deflection curve is like this. This point is here. If you draw the tangent from the left hand side, or you draw the tangent from the right hand side, the two tangents should have the same. The two tangents should have the same value. Okay, that is what is here. The two tangents at this point, at point B, not at point D, should have the same value. Slope should be same at point B. Okay, because the deflection curve will essentially be like this. The deflection curve will essentially be like this. Okay, so if you draw the tangent at this very point, whether you draw the tangent from the right hand side or you draw the tangent from the slope of the tangent should be same. That is, slope of the tangent is given by d nu by dx at x is equal to 2 meter given by the equation applicable on the left hand side should be equal to the slope of the tangent given by the equation at x is equal to 2 meter should be same as given by the equation applicable on the left hand side. The two should have the same tangents. That means if you substitute the value of x is equal to 2 in this equation, substitute the value of x is equal to 2 in this equation, okay, and substitute the value of x is equal to 2 in this equation, okay, substitute the value of x is equal to in this equation and substitute the x equal to in this equation. Okay, so x is equal to 2, it will be 4 plus c1. X is equal to 2, it will have some value plus c3. The left hand side should be same. So therefore you will obtain the equation between c1 and c3. Previously you had an equation that's what's given here. That's what is given here. This is one equation, this is another equation. Now previously also, not only this, as it said, not only the slopes, but the values of the deflection are also same as discussed right now. That the value of the deflection given by the equation on the left hand side should be equal to the value of the deflection given by the equation applicable on the right hand side. That is, we mean to say that is the deflection given by the equation applicable on the right hand side, the value of the equation, the value of the deflection given by the equation applicable on the left hand side, that is this, should be equal at x is equal to 2. This should be equal to the value of the deflection given by the equation applicable on the left hand side, applicable on the right hand side at x is equal to 2. That is fine. So in this equation, and in this equation, you substitute the value of x is equal to and make the equations equal. You will get the relationship between C1 and C3 and C4. So we have more than enough equations now to solve. So one of the equation we have, this equation we have in between C3 and C4. This equation using this boundary condition we have in terms of C1 and C3, and this equation using deflections at x is equal to 2 we have in terms of C3 and C4. Now what we need to do, so we have all these equations now in hand. Okay, solve these algebraic equations, you will obtain the value of C1. C2 we have already obtained equal to 0. We'll obtain the value of C3 and we'll obtain the value of C4. So these four constants of integration, after obtaining using all these boundary conditions, we have to substitute back. We have to substitute these equations back in the deflection curve equation, that is EI nu 1 by 3 C1 1 by 3 x1 plus C2 is equal to 0, and we'll substitute the value of C3 and C4. We'll obtain the value of the deflection as given by the equation applicable on the right hand side. So this is how we will be obtaining these equation values. We'll be obtaining these deflections, we'll be obtaining the slopes and the deflections. We will go ahead in a while from now in next class.